I am Anil Kumar. Welcome to my series on calculus. In this video, we'll discuss curve sketching. One of the key parameters to understand is a set of key points. These are four very important points for us to understand. So before getting into details of curve sketching, let us try to understand what are critical points, what are stationary points, what are saddle points, and what is a point of inflection. We'll also take up an example to elaborate on the same. So let me first begin with giving what these points are. Critical point. What do you think is a critical point? Well, critical point is a point where the derivative is zero or it does not exist. So critical point has two conditions. First is that the derivative is equal to zero, first derivative, and the second is that it could be does not exist, right? So these are the two conditions which could lead to critical points. So the condition clearly here is or, right? So it could be either one of these two things. Now let's see what is a stationary point. Stationary point is a point where the derivative is equal to zero. Now with that, that particular point could have a local maxima or a minima or neither. Now it's important to understand that if the first derivative is zero, it means it could have a local maximum, a local minimum, or neither of the two, right? Now what is a saddle point? Saddle point also is a critical point where the first derivative is zero. However, at this point, we do not have maximum or minimum. So it is a condition where we do not have local extrema. That is important, and what we have here is kind of a saddle. So that is the saddle point, right? So derivative definitely is zero, since if you draw a tangent line at this point, it will be horizontal. It will cut through the graph, right? So we have a horizontal tangent, as you can see. Through curve. Perfect. Now this could be also referred as a point of inflection. However, point of inflection is more than the saddle point. What is a point of inflection? For point of inflection, we say that the second derivative is actually equal to 0, where concavity changes, right? So we get the first three from the definition of first derivative. And the second one is from the definition of the second derivative. Do you see the huge difference? So saddle point may give you something which has a point of inflection. However, the criteria is different. So I hope you understand this fine point. Now to elaborate more on this, I have taken a specific example which we will also take. Perfect. Now first, let me take an example with the help of a graph to illustrate what could be a critical point, which is a stationary point, not a saddle point, what could be a point of inflection, but not a saddle point. Let's take those kinds of examples with the help of a graph. So here again, I've copied the same thing, but my approach is going to be very different. So let's now consider a graph. So I will just draw random graph here, and we will consider different kinds of points on this particular graph. So let's say we have a function which is kind of like this. Okay, just made a function which is kind of like this. And the critical points which we are going to check are these. Some of them, let me mark. So all seem to be different, but this is very different, right? We'll call this as a point, not as a sharp point. And here we can say is change of concavity, right? Okay. So we're marking these points as A, B, C, D, E. Let me call this point as F. So for this particular discussion, we'll just consider these few points. Now, our definition said that the critical point is where the derivative is equal to 0 or it does not exist. So in that case, which points qualify? Well, all of them will be our critical points and we will list them all. So the critical points are A, B, C, D, E, and F. Is that clear to you? Now, stationary points are the points where the derivative, first derivative, is 0, right? So in that case, what are the points? Well, all except F, right? So what we get here is the point which is for us A, B, C, D, E, but not F. See, at F we have a sharp corner, and that is why that has to be excluded. You get the idea, right? So this is a corner. You can also say a cusp. So here, so the derivative does not exist, and therefore it is a critical point but not a stationary point. Is this point clear to you? Now, saddle point. So out of these, the saddle point is E, where the derivative is equal to 0. However, we have neither maxima nor minima. So that is the saddle point, E. So the example for saddle point here is E. Is that clear to you? Now, point of inflection. Now, when we say point of inflection, there are a couple of points which are point of inflection for us. Now, okay, the C is also not there in the stationary points. That was wrongly written. Okay, A, B, D, E, these are the points which we are considering as derivative is 0. The C derivative is not 0. Okay. Now, point of inflection is a point where the second derivative is equal to 0. One thing. Second thing here is that the concavity changes. Two things. So that is very, very important criteria for us for point of inflection. So if you see, the point which qualify is C and E, for example. Now here the concavity is changing. It is going from concave down to concave up, right? So, and at E also, it is from concave down to concave up. So both these points are point of inflection. Clearly, you have seen that the saddle point and point of inflection are different. Perfect. If you have a vertical asymptote, it is possible that the second derivative is 0 and you have a point of inflection. So we'll elaborate this with the help of an example. Now this is a very important example to understand. So I've given the heading as analysis of important points in curve sketching, and we've just taken one example here, which is list the type of points that will be on the curve of f of x equals to x cubed plus x. So let me rewrite the function, which is f of x equals to x cubed plus x. Derivative of this particular function is 3x squared plus 1, and the second derivative for this particular function is 6x. Now clearly, if you want to analyze, let's first analyze the first derivative. First derivative f dash x is equal to 3x squared plus 1. It has no critical points, right? It is never 0, right? And therefore, we have no critical points. Do you see that? Very important to understand that this function does not have any critical point. That means what? That means we do not have no saddle point. Do you get the idea? Let's get back to the definition. So here we were saying saddle point should have first derivative as 0. Now that condition should be met. So what do you see here? Since the first derivative is not 0, we do not have any saddle point. Clear? Second derivative, f double dash x equals to 6x. If you want to equate it to 0, it gives you a value x equals to 0. Now if you analyze this particular point x equals to 0 for the second derivative, what do you get? So that is 0. If you test with a negative 1 on the left side and positive 1 on the right side, then we know that the second derivative is negative and here it is positive. Negative means that the concavity is going to be concave down, and positive means concave up, and that clearly means that we do have a point of inflection at 0. So that means we have a point of inflection at x equals to 0. So you notice that we could have a point of inflection but not a saddle point. You get the idea? So that is kind of important to understand. Okay, now let's move forward in working with critical numbers now. Now the question for you is, determine the critical numbers for each of the following functions. What type of critical number is located at x equals to 5? So we will only analyze one particular point, which is x equals to 5. The other points you can analyze, right? So when we say determine the critical numbers for each of the following functions, what type? When I say type, what does it mean? Type will mean local maxima, local minima, or neither. Do you get the idea? First derivative analysis will give you that. Then we could also have saddle point and all those things. Perfect? Okay. Let's take examples one by one as we move along. So the first one here is f of x is x minus 5 times x plus 2. The second one is, now note here, let me write it bigger and bold so that's very clear to you. The first function f of x is given to us as x minus 5 times x plus 2. Now the second is the derivative. The second one is h dash x. It is not the function, it's the derivative of the function, which is x squared plus 1 times x minus 5 times x minus 1. Do you see that? And the last function here, a of x, is a function itself, absolute function, absolute value of x minus 5. So these are the three examples which you need to consider, and then we'll talk about the extended example. So let's take them one by one. So the very first one here is determine the critical numbers for each of the following. So we have taken the first one here. And question same, what type of critical points is located at x equals to 5? So when we are given the function, we need to find its derivative to find the critical numbers. Derivative of this, how will you figure this out? Well, one easy method is, let us first expand it. So instead of getting directly to derivative, let's figure out what the function is. So we have x minus 5 times x plus 2. Let us expand using distributive property. So we get x squared plus 2x minus 5x minus 10. Combine the like terms and you get x squared minus 3x minus 10. Is that clear to you? Now it is better to find the derivative. So now let's find the derivative of the function. Derivative will be, we are differentiating this now, will be 2x minus 3. Now it is time to find the critical number. So to find the critical number, what are you going to do? For finding the critical number, we have to equate the first derivative to 0. Now, if you equate first derivative to 0, you get 2x minus 3 equals to 0, or x is equal to 3 over 2. So we have only one critical number. Now we need to analyze what type of critical number it is. Now to analyze, we could do a couple of things. So we'll now analyze type. Many things you could do. You could just check it using the intervals. So we have a critical number here which is at x equals to 3 by 2, or you can say 1.5. So I can take a point on either side. One could be 2 and the other one on this side we could just take 0. Okay. The function for us is the derivative, which is derivative is equal to 2x minus 3. Now if I substitute 0, what do I get? 0 gives you minus, let me draw a line here, and plus 2 gives me a positive number. That clearly means that the function is decreasing and then increasing, right? And so we have a local minimum. Does it make sense to you? So we have a critical number and we can now write down our answer, which is critical number is x equals to 3 by 2, and it represents a local minimum. Is that clear to you? So that is how we should be answering this question. Perfect. Let's move on and take the second example now. So I hope you have understood the concept. Now in the second example, we have directly given you the derivative, right? Since the derivative is given to us, we can straight away write when is this derivative equals to 0. That is to say, when is x squared plus 1 times x minus 5 times x minus 1 equals to 0. Well, the first factor will never be 0. We get x equals to 5 as one of the answers, and we get x equals to 1. So these are the 2 points where we have zeros, and therefore we can now write down that we have two critical numbers. So the critical numbers, let me write it like this, are at x equals to 1 and x equals to 5. Now we'll consider the type of critical number, right? So let's say now the type of critical number. So when you want to find the type of critical number, we need to analyze the first derivative. Now, how will you analyze the first derivative? Well, same method as we did last time. So we'll have two critical numbers. These two critical numbers are going to divide our plane in three parts. These two critical numbers are at x equals to 1 and x equals to 5. So we have these planes now. We can take a test point. Let me write down test point here. Test point could be 0, could be 2, and could be 6 in the given intervals. The factors for us are x squared plus 1, x minus 5, and x minus 1. When you substitute these values, what do you get? For substituting, x squared plus 1 will always be positive. And for x minus 5, these values will be negative, but that will be positive. For x minus 1, we have negative, positive, and positive. Now, combining all of them, we get positive here. That means the first derivative is positive, first derivative is negative, first derivative is positive. Positive means that the function is rising. Negative means function is decreasing, and then again rising. So clearly we get our answer, and that is at x equals to 1 we have local maxima, and at x equals to 5 we have local minimum. Is that clear to you? So the type is very clear. So we have local maxima at x equals to 1, and we have a local minimum at x equals to 5. Is that clear to you? So that is how you could use your table to analyze the situation. Now let's take the next example. In this case, we have absolute function. Now let me sketch the function to make it very simple for you. The absolute function is absolute value of x minus 5. That means that the absolute function has moved 5 units to the right. Perfect. So that is the absolute function. At 5, we do have a critical point. So let me write down that we have a critical number at x equals to 5. Reason is it is a corner where the first derivative does not exist at x equals to 5. Clear? Perfect, right? First derivative does not exist. However, that becomes a critical number since it does not exist. Does not exist means a critical number. So when you say that the first derivative is 0 or does not exist, we get a critical number. So we do have a critical number here. Perfect. So that is what is very important to understand. And at this critical number, we have a local minimum. As you can see. Now, if you check the derivative of the function in the piecewise function, so what we have here is basically a piecewise function. So you could actually write this particular function a of x, let me use a different ink, write the function, and then we'll find the derivative. So let's say we have this function, okay, a of x, which is written as x minus 5 for x is greater than equal to 5, but it is negative of x minus 5 for x less than 5. That is how you define this particular function, correct? So the derivative of this function is on the left side, this is the right side. On the right side, it is, you can see positive 1 when x is greater than, not equal to, but greater than 5. But it is negative 1 when x is less than 5. And therefore, at 5, it does not exist. Now, since it changes from negative to positive, so it changes from negative to positive. We have local minimum. Is that clear to you? So you could algebraically prove that this is a local minimum. And that is very important for you to understand. Clear? So the idea here always is when you have an absolute function, write it as a piecewise function. Perfect. And then get your result. Now here is the last example, which is a general example. We are saying find critical numbers for the function g of x equals to x minus a to the power of p times x minus b to the power of q. So let's figure out what is g of x equals to. So we are given the function g of x equals to x minus a to the power of p times x minus b to the power of q. Last time when we were working with a quadratic function, we expanded, right? So I hope you remember we expanded. Now when we have a function which is like this, it is not easy to expand. It is better to use product rule and find the derivative. Correct? So we'll have the derivative of the first function, which is p times x minus a to the power of p minus 1 times the second function, which is x minus b to the power of q, plus the first function as such, which is x minus a times derivative of the second, I'm writing q here, x minus b to the power of q minus 1. So we use product rule. So we use the product rule to find the derivative, right? So this is using product rule. Now the critical number is when this derivative is 0. So let's equate it to 0 to find the critical number. Perfect. So now to analyze this, we should factor. We can write this as we have x minus a to the power of p minus 1 as a common factor. We have x minus b to the power of q minus 1 as a common factor. And what we get here is p times x minus b plus q times x minus, this is to the power of p, x minus a, since we have taken one less power as a common factor. And all this is equal to 0 to find the critical number. Perfect. Now that gives you, let me go one more step so that I can actually simplify this also, right? And then we'll write down all the critical numbers. So we have our equation as x minus a to the power of p minus 1 times x minus b to the power of q minus 1. And inside the brackets, we have px minus pb plus qx minus qa equals to 0. So we have x minus a to the power of p minus 1, x minus b to the power of q minus 1. And here we could actually factor out x and write down this as p plus q, and we are left with minus pb plus qa. Perfect. So that is what we get. Now the critical numbers, let me write down in red ink. So from here we get x equals to a, that could be 0, x equals to b, perfect. And from here x equals to, when you equate it to 0, this thing goes to the right side. So we get pb minus qa, and then you divide this by p plus q. Perfect. So we have these as our critical numbers. Is that clear to you? So we have three critical numbers as mentioned here. So one of them is x plus a, the other one is x equals to b, and this whole thing, that is the critical number which we have. So that is how you're going to solve it. So with that, we come to an end of very important concept where we have learned what is a critical number, what is a stationary point, what is a saddle point, and what is point of inflection. And clearly, we could differentiate between these things, since the important thing for a critical number is that this could also have the condition of does not exist. Now that condition gives you graphs which could be of the form like this, right? Or like this. Is that clear to you? So those points are the ones where the function derivative does not exist. For stationary point, that derivative has to be 0. So those are the differences. For a saddle point, it has to be zero, but not a maximum or minimum, right? So saddle point is never a local maximum or a local minimum. So criteria is to look into the local extrema to differentiate between these two. And as far as the point of inflection is concerned, you have to look forward for the second derivative. We're actually not concerned with the first derivative. It may be zero, may not be zero. It doesn't make sense. So these two are entirely different things. To look at it, you could say that saddle points are point of inflection, but not the other way, right? In the example itself, it was very clear that we have a point of inflection, right? We have a point of inflection here, but we have no saddle point since we did not have any critical point. So that is key. Now, when it comes to a general question as shown here, in that case, you have to expand using the product rule and then simplify to get your answer. And we get three answers in this case. And the answers are x equals to a, x equals to b, and x equals to pb minus qa divided by p plus q. And that is how we are going to solve this. Some of these questions are from test papers. I hope you understand and appreciate it. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.